I also hope that my screen is visible. Yes. So is my screen visible?
Yes, sir.
Okay. So I think then we are in a good condition to start for today's class. So in the last class, we were discussing about, right, sizing a chain of inverters, right? There we have introduced a parameter which is called gamma, right? And we have seen that we have how to represent this internal capacitance or the self-loading capacitance in terms of its gate capacitance, right? Because this self-loading capacitance will be a part of this the driving gate itself, right? And we have seen that for mm, modern submicron technology, this gamma can be assumed to be as 1, right? So we have taken that, and from there we have started from with this assumption, like this gamma is nearly equal to 1. Maybe in some cases we will not just substitute the value of gamma, we will keep the gamma as it is only, and then we will move on to our this analysis and see like what would be the condition so that we can get the delay for, or we can make the delay of this inverter chain minimum, right? So for example, here we have started with this one, like we have assumed that this is the load capacitance, this is the load capacitance, the CL. This has to be derived by this n number of inverters. Here this n may be odd, n may be even. So right at this moment, do not worry about the polarity. Polarity means, if you know, if you have number three stages, if you have odd number of stages, then whatever the signal you are getting giving at this input, then you will get back that signal. But if you have the even number of signal, you will get the your, it will be like the opposite, right? It is not the expected output from that particular inverter. So that at this moment, do not worry about that, the polarity of whether it is for right 0 to 1 or 1 to 0. We will take it up in a later stages. Right. So here we have considered, like, let us consider a particular stage, say this jth stage. So for this jth stage, what would be the delay? So we know, so for jth stage, this would be the delay where this TP naught is the intrinsic delay. And we know this would be the output capacitance for this total. And this is the gate capacitance for this. Right. So from here, we have substituted from here, what is the then total delay? Total delay would be the summation of all this delay. Now we have to minimize the delay. So how can you do that? Just you have to take this n minus 1 partial derivative and make this each derivative equal to 0. So if you do that for jth stage, you will get that this condition. That means Cg of j would be equal to this is would be equal to root over of this Cg of j plus 1 into Cg of j minus 1. That means it is the geometrical mean, right? So similarly, if you do for j minus 1, then okay, j minus 2, j plus 1, j plus 2, similarly you can get this type of this criteria, right? Okay, now so if you know this criteria, then what is the overall fan out? Okay, then finally the thing is that we have to find the total delay, so we are approaching towards that. So right here, what is the total overall fan out? Overall fan out means this C load that we are driving by the initial gate capacitance, which is Cg1, right? And this particular factor actually, it can be written in this way. So here, it basically, you can write the CL by CG1 actually like this, like this, like this, like this, like this. And if you see from here that this each of this term, right, each of this term is equal to the F, or the sizing factor from one consecutive stage to the next consecutive stage. So that means if the size is here 1, then for the next stage, the size would has to be increased by F times. So it is 1 into F. So it is F square. So the next stage, it has to be this this F into F. So it will be F like for 1, if it is 1, when size is 1, and here next stage it will be F, third stage it will be F square, and so on. Right. So here, this is F, this is also F, this is also F, like that. There n times of n F will come. So that is basically this F is equal to F to the power n. So I hope that you have gone through this part, and now I think no need to tell, like F is the overall, right? This overall fan out, and this F is the effective fan out. Effective fan out means for each stages, overall means for the total chain, right? So from here we can see that F should be equal to the nth root of this F. So this is the basically the criteria. Okay, if we follow, make this F, that is the effective fan out is the nth root of the overall fan out, then we will get the delay which is minimum, right? So we now know the, we now know like what should be the criteria for this. Then if you have to write the total delay, then you can take it, we can take it from here, right? So it is basically TP naught. So let me write it here. So the overall total delay would be equal to what? This would be equal to TP naught summation of this j equal to 1 to n 1 plus Cg of j plus 1 by this gamma of Cg of j, right? So here this would be the criteria total, like TP would be equal to this one, right? Now we have also seen like these factors, if you just keep on adding, so that will basically, and this is the summation, right? So there are nth stages, so obviously you will have n term here, and this will result what you can see from here. This is actually root of n, so it will be n times of root of n, right? So you can take this n common, and you can write it like this. This is 1 plus 1 plus nth root of f by gamma, right? Just simply, you can just keep this, put these values here, and you will get this. So this is the total delay if you want to represent. So total, total delay obviously, and this is the minimum delay, right? Because we have already put the condition. This is the condition for this minimum delay. So here what we have done, please try to understand that here we have not considered what should be the number of n, right? We have considered what should be the criteria of scaling, right? From one stage to the next stage, right? We have considered that, right? From that, we have come to this, right? So this is the total delay that we are getting where this n is fixed. Now the question can be also asked, what would be the number of n? Suppose if you have given for, say, this previous problem only, then how many stages you will choose, whether it is 5, 6, 10, 20, how much? Right. So again, to do that, what we have to do, so now we know this is the total number of, this is the total delay, right? So the total delay, again, this expression has to be, they have to do a derivative in terms of this n, right? And then from there, you have to find what should be the criteria for n to get the minimum number of delay. So here, we are continuing from here. Right, you can choose here now we are trying to choose the right number of stages. So right number of stages is basically the number n, okay, in an inverter chain. So there are n number of inverter chain, and for this we have find this minimum delay, okay, minimum delay, okay, after scaling, or yeah, you can say after scaling, because that is also not wrong to say, because scaling means we are scaling it by a factor of f. So if we do keep on scaling this f, then this is the minimum delay and this is the criteria. But what should be the criteria in terms of this n, right? So for that, what you have to do, you have to take another derivative with respect to this n. So you can, do this. So this is not that way difficult. Only thing is that here we have to know what should be the derivative of this. Anyone? What should be the derivative of ddx of a to the power 1 by x? Because this is f to the power 1 by n, right? So what is the derivative of this? Okay, this is basically a to the power 1 by x ln of a by x square, right? So just use this one here and you will get the expression. So the final one, if I have to write, so it comes out to be gamma, the final expression, gamma plus nth root of f minus this nth root of f ln of f by f, that would be equal to, right? So for minimum delay optimized n, right? When you optimize n, then what you have to do, you have to make this term near equal to 0. So when you make this term equal to 0, then you will get this expression, right? So after making 0 only, you will get this one. Okay. Okay. So this one, if you try a little bit, try to manipulate this a little bit further, then from here you will see that you can actually write this expression in terms of the small f, where it is 1 plus gamma by f. I encourage you to please check this out, how you can do that. And I think in this context, if you want to really check it, what I personally felt, if you try to go from this line to this line, or try to derive this expression from this expression, compared to that, if you try to derive from this expression and try to go to this expression, it would be easier. Okay, please try that. Please try to expand this and see whether you are getting this expression or not. Right, just to proving like whether these two expressions are same or not. Right. So if this is the correct expression, okay, for optimized
Sir,
number.
in exponents, what have you written? 1 plus x
Oh,
by f.
1 plus, sorry, it is not x actually, it is gamma. Okay, it is gamma. This gamma. Okay, so it is this gamma from here, right? So, but here if you want to see, like, how should, okay. So this expression is basically relating this f, that is the effective fan out, right? And the relation between this gamma, right? And you can see this expression, right? This expression you cannot possibly solve, okay, in a regular fashion without, it means without using any iterations, right? Means without any numerical solution, you cannot get a relation between f and gamma. Only, except only one case, say like to make, if you make gamma equal to 0, right? When the gamma equal to 0, so it is basically exponential of 1, right? So this is basically exponential of 1. And what is the value of exponential of 1? 1 is 2.718, right? So only for this, you can just understand that it will be around 2.718, right? And if you plot it, okay, so suppose if you have done the simulations and okay, and solve it numerically, and if you plot it, so it is the f optimized. Okay, we also try to optimize the value of f from here, and with respect to this gamma, so for means here, because this is the relation between f and gamma, so we want to see that we know that gamma equal to 1 for all submicron devices, right? So for if this condition holds true for submicron devices, then we would be interested to see for gamma equal to 1, what is the value. So if you plot actually for different gamma, this plot would come something like this. Okay, and here you can clearly see for gamma equal to 1, the value comes around, how much it is, comes around 3.6. It comes around 3.6. Okay, so then from this perspective, typically we will say like f optimized equal to 4. So please try to understand what we are trying to do from here. Here, this f, this is the effective fan out. We are trying to expressing, means we are finding this expression for minimum delay, okay, for a known value of n, right? Again, what will be the value of n, right? We should first answer that, right? Because this f is fixed, right? F is this output by input capacitance. Then what will be the value of this n? That value of n, okay, we have arrived from here, right? That big okay, why why we are arriving from this or from which angle we are trying to find this. See from here, f optimized, if this f optimized is nearly equal to this 4, right, then you know what is my C1, what is my Cn, that means the first capacitance, and what is my load capacitance, right? So you know this too, right? So from this, you know what is this capital F, right? Now the question is how many would be the total number of n. So for that you should try to make this F, right? That means like a scaling factor from one inverter to the next inverter nearly equal to 4, right? So you make that nearly equal to 4, and depending on that you choose the number of stages. Okay, suppose if I choose n equal to 4, and that will help me to make f close to equal to 4, then I will choose f equal to n equal to 2. Okay, so suppose if I choose n equal to 10, probably that would make f like much less than this 4. Okay, which is again not an good optimized way to design it. Okay, so try to get an idea of what should be the value of f, okay, for the number of n you are using. And we have seen from here that generally we try to keep this optimized value of f nearly equal to this 4. Okay, so from that perspective you can like design the number of stages, how many stages you want to put in between. Okay, so and here you can see this total, like the normalized delay. Normalized delay is what? Normalized delay is basically this TP by TP naught. Okay, TP by TP naught. That's why you are making normalized, right? So normalized delay would be equal to, if you plot it with respect to this F, then you will get some plot which is like this. So here the total intention of why I am showing this, because you can see if you are taking f is equal to 4, or if you are taking f equal to 3.5, or if you are taking 4.5, or even if you are taking 5, right, or even if you are taking f equal to 3, see the propagation delay, it the dependence of propagation delay, okay, for this range of f is not that significant. Right. So for this much, for this range, you can choose like any value of f. However, try to keep this f as close as possible to this number 4. Is this clear to you? Okay. So then let us try to do one example. Okay. Here. So here we are not choosing what should be the total number of n, because it is already been given that the three total number of inverters, here it is given n equal to 3. It is already given, right? So it is C in, and CL is given as 100 of C in, right? And here we have asked, means in this question it has been asked that size each inverter to minimize the delay. So you have to size this inverter, means you have to find the F. Okay, so for the C in we cannot do any change, because this is the initial stage, so we cannot do any change here, right? Because the capacitance is fixed here. Okay, now from the next stage onwards we can do that. Then mention the transistor sizes. So here you can see this WL1 on like WN1, WP1, WN2, WP2. These are mentioned. We need to find this. Okay, what would be the width? Size means basically the width, because for a particular technology, L is constant, right? And we and they have also mentioned that W1, that is WN1, that is width of this NMOS for the first stage, is equal to 1 micrometer, and it is also given W mu p, that is the mobility of hole, is half of that of electron, right? So from this perspective we need to approach. So yeah, can you suggest like what should we do first?
Calculate the fan out.
Right. So calculate this fan out. So basically it should be the like F, capital F, right? Basically this output by this input load, right? So it is basically C in by this one. So if you do that, it basically comes this 100, right? N is already fixed here. N is equal to 3. Okay. So N is already 3. Then you need to find what is this effective fan out. Effective fan out means for each stage fan out. Okay, to get the minimum delay. We know to get the minimum delay, the condition, the criteria is this, right? So this should be 3 like this, right? Which gives us to 4.64, right? Okay, so we'll keep it like this only. F equal to 4.64 only. We are suppose we are not changing it to 4. Okay, we are keeping this F is equal to exactly to this because this is the scaling factor. We can change it, right? Means we can change it. We can make width equal to 4.6 micrometer, 4.64 micrometer if we want. That should not be an issue. Right. So this is now the scaling factor that we know. Now we have to find the what is the transistor sizes. Right. To find the transistor sizes, what we have to do for the first one, second one, third one. So for the first one, we have to find. So for the first one, width is already mentioned as WN1 equal to 1 micrometer, right? And it is also mentioned that mu P equal to half of mu N, right? Now you know we have to make the charging and discharging time symmetric, right? So this resistance and this resistance has to be same. PMOS resistance and NMOS resistance has to be same, right? If you have to do that, then you have to make this PMOS with 2 times of that of NMOS with, right? Because of this condition. And if you have understood this, then definitely you can say WP1 would be equal to 2 micrometer, right? To make charging and
Sir, can't we
discharging.
use beta equals to root R?
Sorry,
Sir, for that minimum delay, beta optimal equals to root R.
beta. Which is what is the beta here?
Sir, during that, sir, in that PMOS and NMOS, earlier we were discussing that.
Oh, okay. Yeah. So for PMOS and NMOS, we have considered that like it should not be this mu p by mu n, but it should be root over of that, right?
Yes, sir.
That part you were talking. Right. But again, yeah, if you want from that perspective, you can do that. But for typically for hand calculations, even for thumb rule also, what we do is we follow this technique only. Okay, just multiply, just make the resistance of these two such that these two resistances are like same. Okay, yeah, you have a point there, right? So then if this is true, all right, then we need to also find what are the values of WN2. So can you help me in finding WN2 and WP2? What should be the width of this NMOS for the second stage? It would be WN1 into F, and it would be WP1 into F, right? So it will be 4.64 micrometer. This would be equal to how much? 2 times of this 9.28 micrometer, right? Then for the third stage, WN3, WP, okay, not ratio. We have to calculate it explicitly. So WN2 and WP2. So this would be WN1 into F square, and here WP1 into F square. So that will give how much?
We are WN3, WP3, right?
Uh-huh.
WN3 and WP3.
Oh, right. These are already you have written too. So this is for the third stage, this micrometer, and for the next one, it should be 41.08 micrometer. So right. So like that, you can actually now means even from the transistor point level point of view, also you can understand, right? If you have to minimize the delay, then you know how you should size like each PMOS and NMOS, right? Right. Okay.
Sir, but in this
Sir,
question we need to minimize the delay, right?
Mhm.
So shouldn't we take the root R condition?
Yeah, you can take a router condition, but do you also recall there was some thing different there? Like, what was the issue if you take it a router?
Charging discharging time won't be same.
Huh?
TPHL and TPLH will have significant
We
difference.
right, exactly. See here, this is right. This is root R, right? For root R, this is the TPLH, all right, and this is okay. Eventually, I have not plotted it. One, so suppose if I have plotted this one here, then this would be the value of TPHL. See the difference between TPLH and TPHL. That is huge, right? So, but we want this TPLH and TPHL to be closely equal, right? So that's what we are taking this one. But you are right. If only the minimization of delay is the main factor, then we have to choose root over of R or root over or this beta optimized, not this one R. Right. But as I mentioned here, we are trying to make this charging and discharging time equal. So we are taking this R. Okay. So is that make sense here? Okay. Right. So then probably we can. So far we have quite extensively focused on the delay, and we have seen how to find delay for this or single stage, I mean single inverter, as well as if it is a chain of inverters. So far we are focusing primarily on the inverter. So maybe probably in the next class we will also try to, or next to next class, okay, maybe we'll also try to focus on the gates. Okay, for example, suppose NAND gate, NOR gate. Okay, what would be the delay if you are considering those gates? Okay, okay. So and how to find that delay, right? But if we have understood this part clearly, then I think it should be fine. Okay, and probably in some cases, the gate might be bit somewhere different. I mean, this arrangement may be somewhat. Suppose here this inverter is driving only one inverter, but in practical case, it might be driving two inverters or even three inverters. Right. Then how to scale? Okay, like from here to here, we are scaling by a factor of f. Then should we also apply here if there are multiple number of inverters are connected at this output, or if you have to do some changes? So those things are a bit different. So you'll take these things up in a later stages. Okay, and eventually it might be not this gate only, NAND gate only. It might be and not an inverter. It might be a NAND gate. Okay, which is actually driving this, not this one. So in that case, how can you find if there is a mixture of multiple gates? Okay, how you'll find the delay and how you minimize it? Okay, so now let us also introduce and discuss some of another important topic. Okay, regarding this context of design, regarding this design context, which is an power dissipation. Power dissipation in a CMOS inverter. So in CMOS inverter, the total power dissipation can be divided into three stages or three different parts. The number one is the dynamic power dissipation. The second one is dissipation due to direct path current. And the third one is the static power consumption. Even though we have mentioned that static power consumption is zero for ideal CMOS inverter, but we will see here that practically we will have some finite amount of static power dissipation even in CMOS inverter. Right now, if there are three components of this total power dissipation in a CMOS inverter, then it is very easy. If you know how to calculate this thing, then what would be the total power dissipation in a CMOS inverter? You have to just add these three, right? So let us now focus on one by one. So what about the dynamic power dissipation? So first, then let us discuss what do we mean by dynamic power dissipation. So dynamic power dissipation is basically the power dissipation due to the charging and discharging of CL, load capacitor. This is the power dissipation due to charging and discharging of CL, right? Now, you know that during this charging, right, that means when this voltage is rising from 0 to 1, right? Okay, so when it is from 0, what will happen? When it is rising from 0 to 1, what will happen to this output?
It will go from 1 to 0.
It will go to 1 to 0, right? Okay, then probably I should do a small change here. So it is 1 to 0, right? So output, I mean, input is 1 to 0. So as a result, output is changing from 0 to 1. So the output capacitor is basically charging. So in one cycle, basically, so here then also I should change. So when suppose the input is this one, input is changing from 0 to 1, or then let me also write output is changing from 0 to 1, right? So for it, okay, for this case, what is the total energy dissipated? Okay, total energy dissipated from this VDD. We have done this exercise, right? So that's what I have written, recall. So we have already calculated this energy dissipated from this voltage source VDD is nothing but this CL VDD square. And we have seen that there are two components, right? The half of the CL VDD square, that part would be dissipated, okay, in this PMOS, right, during charging. And this another half, that is half of CL VDD square, is basically stored in the will be stored in this capacitor, right? Then in the next half, that means when this capacitor discharges, then this amount of energy is also dissipated in this NMOS, right? So but if you see for this scale, means when the output is changing from 0 to 1, for this case, right, for this case, the total energy dissipated, okay, or the total energy taken from this VDD source is nothing but this CL VDD square, right? Now we are trying to find what is the power consumption. So if you have to relate with the power, then this is for one like this is for only one cycle, right? Then we have to multiply it with this some time factor, means we have to introduce some time factor, right? So power is basically energy dissipation per unit time, right? So then what would be the power? So the power would be this dynamic power is this CL VDD square per unit time. So per unit time, how many cycle? So that basically gives what is the frequency of changing this output from 0 to 1, right? So this is a very simple way by which you can estimate what is the power dissipation or the dynamic power dissipation in a CMOS inverter. Okay. So, but you then here notice one thing a bit clearly, that this power dissipation, right, that is this P dynamic, is related with this VDD square, right? So that means if you change this VDD, right, if you change this VDD 2 times, the power dissipation will change by 4 times, right? Dynamic power dissipation changes by 4 times. So this VDD has a huge impact on this dynamic power dissipation, right? So that thing we have noticed. Okay. Okay, right. And also one more thing, what about this part? What about this part, right? The frequency. This is the frequency. Frequency means how the output is changing. So this is again related to the clock that suppose if you're considering and any digital circuit, so there will be some clock, right? So that clock frequency will determine, okay, how fast the output will change. If all the transistors in a particular IC, is driven by the same clock, and so the output also has to be changed, okay, at a same rate as this clock frequency only. And the clock frequency increases from one technology node to another technology node, right? Because when you sync the device, right, you basically reduce the delay, right? Delay in the device, right? So the device can be now operated in a much faster fashion, right? So basically this you can further increase the clock, but when you further increase the clock, see what is happening. This the dynamic power dissipation is also directly proportional to this frequency as well, right? Okay, but at the same time, when you are scaling means we are reducing the device dimension. What is happening to this FDD? FDD is also falling. So FDD falls with scaling, right? Because you need to reduce this FDD so that the device can withstand that voltage. So FDD falls, but if not increases. But when we will discuss this scaling in more detail, you will be able to see that this FDD, this VDD really does not fall in a that sharp fashion. Okay, for many technology node, we will observe that this VDD, the change in VDD is almost very insignificant compared to the change in this if not. So we will arrive some situation where basically the total circuit performance would be limited by the dynamic power dissipation because of this very high clock frequency. So probably that will also restrict us, like why we cannot go any more or any further increase this clock frequency, right? But here one good thing is that, right, suppose if you have 1 million IC or 1 million inverters, okay, say 1 million inverter in a particular IC, not all the ICs are switching at the same rate as that of this clock frequency. Some some inverters are switching at the clock frequency, some inverters are not, right? So to indicate that, what we write? We write P dynamic is equal to CL VDD square, if not 0 to 1, into this we multiply with a probability factor of this 0 to 1. So this is the probability factor, okay, that indicates, okay, how often the output changes, okay, from 0 to 1, because when the output is only changing from 0 to 1, then only the power is getting consumed for this dynamic power consumption, right? So we introduce this probability factor. This probability factor is also called this switching activity. Okay, how fast or how often this output of this particular gate is getting switched. Okay, so to demonstrate that, suppose this is the clock. Okay, this is the clock that you are feeding to this system. However, say for this particular inverter only, the particular inverter output changes like this, right? So now then what would be the switching probability or the switching activity for this? So here, see, what is the total number of clocks that we have given? So 3, 4, 5, 6, 7, 8. So 8 number of clocks we have given, but see how many 0 to 1 changes are here. These 0 to 1 changes are here, one, here this 1, right? And here this 2. So like, right? So it is basically 1/4. So the, if you have to find the transition probability, so the transition probability is 0.25, right? So that way here the switching activity would be 25% or 0.25 here, like for this particular gate. So you should also know like what is the switching, switching activity or switching factor for an inverter. Okay, in a particular IC, right? So I think we have discussed couple of things here. So please note the effect of scaling, on VDD and on the clock frequency, right? And its impact on P dynamic, right? Next, we have also discussed about the probability factor, right? This introduce this probability factor, right? Or transition probability, which is also called the switching activity. So this will give you some idea about like how to estimate, right? Or basically what is the expression at this moment, what is the expression only, right,
So what have
of
you
this.
written? VDD and
Sorry,
effect of scaling on VDD and
VDD and okay, VDD and clock frequency, this F naught 0 to 1. Fine.
yes, sir.
Okay, then I think they here in this dynamic power dissipation, more or less these things are important. Okay, for so for our like for inverter purpose. Okay, we will see if we have to discuss something extra when you are discussing some additional gates like NAND gate, NOR gate, right? For this. Okay. Now, dissipation due to direct path. So what does this mean? Right. See, so far we have considered the input is like type of step input, right? So that means it changes from 0 to 1, like all of a sudden. So similarly, the output changes from 1 to 0, like that instantaneously, right? But practically, this is not the case, right? So if it is suppose the input and output is like this, so that means, so if this transistor is off, PMOS is on, then this is off. If this is off, then this is on. Not both the same means for this input, never both the transistors would be in a on state. However, if you consider the practical case, so practical case, the input would be like this, right? Practical case input would be like this. So input is this green line. So the input changes, with some finite time. It needs some finite time to reach from this 0 level to VDD level, right? Again, when it has to fall, okay, then it needs again some finite time, like to go from VDD to 0, right? Right. So I hope that you also recall that for this inverter, the VTC or the voltage transfer characteristics looks something like this, all right? And if this is the case, right, not the ideal one, but not this step input, but this type of ramp, and then it's basically saturates to VDD. If the input is like this, which is a quite practical case, then you can see like during this stage, all right, you are changing this V in like gradually. So when you are changing this V in gradually, we know that during here, right, this region of operations, both the transistors would be on, right? I hope that you can recall this. So here, both NMOS and PMOS, they are on, right? So if both of this NMOS and PMOS are on, so that means what? So this is on, this is on. So there now exists a direct path, right? So there exists a direct path from VDD to ground. So from VDD to ground, there is a direct path. So this direct path, basically, then you will have some current, right? And that also we have discussed earlier in different contexts, and we have seen like the current would be right. This is the drain current that would flow, and that would look like this. So if we try to simplify, for our like hand calculation and try to find what would be the power dissipation for this, right? Then you can see this is the VT level, and say like VT of PMOS and NMOS, okay, they are same. say Vt of NMOS and Vth of this PMOS, they are same in magnitude. Okay, then what will happen? Right, I am saying this as a Vt level. So this is Vt level. This is VDD minus Vt level because this is this level, right? This is VDD. So this is one threshold voltage below. So it is VDD minus VTH level, right? So you can see like for between these to this, right? The both the transistors are on, and we have seen that how the current will flow like this in this region. So let us assume not this has not like this means, but it's a straight line, and say like it has a peak value of here. Okay, so we are saying that the current would flow, okay, in this region like this, okay, with a peak value of say like I peak, right? So the peak, this magnitude of this current is I peak. Okay, okay, and we will also say this time duration is T of AC. T of AC stands for the short circuit, like the time period during which you have a short between this VDD and ground. So to represent that, this T of AC, right? So then we need to find what would be the energy consumed in part switching. Part switching means in the like in the as well in the rise part as well as in the fall part. Okay, so like how can you calculate it? See, the energy consumed per cycle here would be, okay, let us first calculate for in the rising part. Okay, what would be the energy dissipation? It is VDD into I peak into T of AC by 2. Please check if you have understood on this not. So basically what I am doing here, so basically we are trying to find what is the area here. So if you, this is the, see, this is current, this is time. If you integrate current with respect to time, basically you will get charge. So voltage into charge, that basically gives you that energy, right? So VDD into I peak T of SC by 2, right? So that gives this energy consumed like during this time, right, from this VDD. And this is the rise part. And during this fall part, again, if they are type of symmetric, right, then it should be also same as this T of SC by 2, right? So that way, like, this 2 part, if they are symmetric, all right, then it would be T of SC only, right? So then this is the energy consumed, in part, energy consumed part switching, right? Now here, what would be the power? Power, if you have to estimate it, then again, we have to multiply it with what? If you have to multiply with the, again, with the clock frequency, right? So that basically will give you like what is the power dissipation, okay, due to this direct path between VDD and ground, right? Okay, right.
So what
So
you said the full form of the TSC, time for switching.
not time for switching. This you can say like the time when both the transistors were on. You see, like for during
Yes, sir.
this period,
That thing
during
I
this
understood.
period, right? During this period only, the both the transistors were on. Shubhayan, is that clear?
Yes, sir.
Hmm.
So, I just wanted to know the full form of SC. TS.
TSC full form. So okay, we can define TSC like that. The TSC is the time, okay, when both the PMOS and NMOS were
Both
on
are on.
simultaneously.
Okay. Okay.
Sir, you actually said short circuit for that.
Yeah, right. So then, okay, see, if we know the input, then from this input we know this, right? We know this, isn't it? So this is say the TS. Okay, this is TS, right? This is the total, like from 0 to this. So how can you find represent TSC in terms of TS? This is not that important, but just wanted to, like, this TSC can be retained. Okay. Yeah, probably TSC. Yeah,
TS into 2
you're right.
VTH divided by VDD.
VDD minus 2 VTH
Yeah,
by
divided
VDD,
by VDD.
DD, isn't it? So that way, if you know this, like if this is given, so you should be also able to find what is this TSC. So you can estimate this power dissipation due to this direct path. Right. Okay.
Sir, why is there a divide by 2? VDD into IP
Divided by
into
2
T.
because like, okay, see, we are trying to find what is the 1 minute. Which color I should pick, because I think all this color we have. Yeah. So if we integrate, okay, what is the area? What is the area of this triangle?
Okay, half I into TSC
Half I peak, right?
into IS
Into
to
TSC,
TSC.
right? So okay, so area is basically what? So this is current, right? This is time. So if you take the then area, so you are basically calculating what?
Yeah, right.
Charge,
I
right?
got it. Yeah, I
So
thought
now
of
you
it as a
multiply with
rectangle. That's why I got confused.
right. Okay, now here one thing is important. What about I? So okay, let us see that this f is the frequency. So frequency is basically the clock frequency. How often, say this is directly connected with the clock, so it does not have much hold on that clock as a design parameter, say. Okay, so what are the other changes probably we can do here? One is again this TSC. So let us say that, yeah, if we can make TSC smaller, then it is better, definitely. VDD, obviously, if you reduce VDD, this power consumption reduces. That is obvious. And see the here the relation is linear. The power is proportional to VDD, not earlier case. Earlier case, P dynamic is VDD is proportional to the VDD square, right? But here this power is proportional to only VDD. Okay, and the other thing is this I peak, right? This I peak also is this one, right? This I peak. Now, what are the other things that we can tell about I peak? So I peak is the peak current, right? So on what parameters, okay, this peak current can be dependent on? First, what about the W by L ratio? If you increase the W by L ratio of each this PMOS and NMOS, then definitely I peak will increase, right? So that is quite clear, right? Because more the width of the transistor, more will be the driving capability, more will be the I peak. Okay. Another thing is, okay, depends also basically on the transistor sizing. Transistor sizing regarding I peak. So here I should write I peak depends on, so I peak depends on this W by L ratio or this transistor sizing. Other very important thing is it is the input and output slope. Input and output slope. See how it is dependent on this input and output. Okay, so this will also, you will understand quickly. See, say for one case CL is high, okay, and we are not changing, and in one case CL is high, in the other case CL is low. Okay, so and both these gates are driven by the same input. Okay, same input means same TS, right? Same rise time, say same rise time. Okay, so in that case, if this CL is high, all right. So for the first case, for output voltage, when this input is changing from 0 to 1, output has to go from 0 to 1 to 0. So that means from VDD to 0. So the change in output would be very slow because of this high CL, right? For this first case. What about in the second case? Okay, let us first discuss for the first case only. So here, this is the input this is the input and this is the output, right? And suppose if we are but if we are drawing on the same time axis, like both of this input and output, and then let us see that what will happen. So say we have started at the same place, right? It obviously has some delay, so we can consider this delay. Right now, let us focus more on this part. Okay, see here. So see, this input has changed from 0 to like VDD already, right? But see, output voltage has changed like very small. The change in output voltage is very small. That means the output voltage is still quite close to VDD, right? So basically, then you have VDD, and during here, when this is here, okay, or any point, say you can say at any point, this here, the output voltage would be very close to that of VDD. Right. Then what is the potential difference between VDD and if this is Vout is also very close to VDD, right? Then the potential difference between these two is very small, right? So that way the current that it can flow from this VDD to ground, that will be also significantly lower, right? That would be also significantly lower for this case. So then I peak is low. Right. However, if you consider the other case, that is here, see here same input, I mean same time it is taking, but say the CL is very small, so this output is falling almost instantaneously. If that happens, see, like there is some delay, and probably no, by during this time only, very small time for this input only, by this time only, output has changed to 0. So this is VDD, and for most of the like time, right, for this input to change, this output is close to 0 volt. So what is the then voltage difference between these two? So the driving capability, but the current that can flow from this VDD for this would be much like higher for this case. Like I peak is high, right? I peak is high. So basically then what can we say, like from this to input output slope, we can say like as we are increasing this output capacitor, right? As we are increasing this output capacitor, this ISC. So basically ISC means overall the short circuit current. So that way you can say like I peak. So basically this is the I peak. So I peak is also falling, right? So the I peak also depends on this input output slope, as you can see from here. Is that part clear to you? Okay. If it is so, then okay, I think it's already one. So the third component is the static power dissipation, right? Probably it is already one today. So we'll take this our class from from the next class onwards. We will start our discussion on this. Huh?
So can you
Static
go to
power
the
dissipation.
upper page once?
Huh?
Can you go to the upper page once?
Yes, yes.
Okay, sir. Okay.
Okay. Sure. Okay. And also, you probably know that, right? Next week we have an like as per the academic calendar, we have an test scheduled, right? So then the for the next week, the test would be again on the probably in the next Tuesday only, no? Because Tuesday we have a 2 hours class, so it would be easier to conduct a test on that day. Okay. So that means on 22. Okay, and the syllabus would be whatever we will cover till tomorrow, including I have already shared one small video with you, which is on CMOS fabrication. That includes, and probably tomorrow also, tomorrow or day after tomorrow, I will also going to share one more video with you. So including these two videos. Okay.
Sir,
Huh.
sir, when CL is high, why are the output characteristics like this?
When the CL is high, why this output will it not be like this? Because then to charge, okay, to suppose if you are not sizing this, if you are not changing the size of this PMOS and NMOS, will it not take much longer time for this CL to get discharged through this NMOS?
Okay, sir. Got it.
right? Okay,
But
if it is
as per-
lower, then it will take very less time, right, to get it discharged, right?
Yes, sir. And sir, on the previous page, uh,
Previous
how did
page.
how
Okay,
did you write the expression of TSC in terms of TS?
how do I represent TSC in
TSC in
terms
terms
of
of TS.
TS? Okay, so TS is the total time. So from 0 to here, this one. And if you consider the total time here, you can see till this VTH, there is no current, right? Till VTH, no current, because they had the one transistor is off, right? And here, if you see for this region, from VDD minus VTH to VDD, again another transistor is off, right? So that both transistors are on only between this region, right? So what we can say then from here, like this region transistor is off, this region transistor is off, this region transistor is off, only the transistor is on between these two regions, right? So the transistor is on only because of this region, and this is the region where the transistors were off. So this VDD minus VTH by V minus 2 VTH by this VDD into TS, will it not give me this VTSC? Ranveer?
Yes, sir. Got it.
Okay. Okay then, so we'll stop here today and we will start our discussion from this static power dissipation from tomorrow. Huh? Okay then, thank you.